We're still looking at optimization problems, and the next example says, find the dimensions of a Norman window whose perimeter is 16 feet and the area is maximized. So we have a perimeter of 16 feet, and we want to maximize the area of the window. And it's a Norman window, which, if you don't know what that means, it's basically you have a rectangular window, and then on top of that rectangular window sits a semicircle. And we're not going to count this right here when we're looking at the perimeter. And we're given that the perimeter is 16 feet. And we want to maximize area again. So let's think about perimeters. So the perimeter of this piece in here, and we need the perimeter of this piece in here. Let's call, because we need the radius in order to find the perimeter of a circle. So let this be R. So if that is R, right, then this length in here has to be actually 2R. I'm not sure what this length is. I don't know what we want to call it, maybe Y. And so we know that the perimeter right now, if we look at just the perimeter of kind of the rectangular shape without the top, that would be the perimeter is equal to 2R plus this 1Y here plus 1Y here. So 2Y plus whatever this circumference is. So recall circumference of a circle, isn't that pi r squared? Person knows that. Sorry, that's the area, which we're going to use too. It's 2 pi r. But we only have half of that circle, right? So the circumference is going to be 1/2 pi r. And we know what the perimeter itself has to be. It was 16 feet total. Okay, so here's part of a constraint. And we want to maximize our area. Well, if I look at the area, I'm looking at the area of, let's say, this rectangular piece, which we know is 2R, length times width. So 2R times Y plus the area of half of that circle. And area of a circle is pi r squared. And so we're going to have 1/2 pi r squared. So the problem here is that we have two different variables in here on our area that we're trying to maximize. We have the variable R and we have the variable Y. And so that's where using that constraint, some information they gave us, and rewrite one of the variables in terms of the other. And so let's rewrite, it doesn't really matter. How about let's rewrite Y in terms of R. Or do we want to, yeah, it doesn't really matter. Okay, so let's rewrite this. Just one sec. Okay, so I have great students that catch me all the time or are good at catching me. You know, I said that circumference of the circle was 2 pi r and we were taking half of it, and I wrote 1/2 pi r. Well, 1/2 of 2 pi r is just pi r. Okay, so we're going back here, looking at our constraint, and we're going to solve for y. So if I get y by itself, let's subtract the others. So we would have 2y is equal to the 16 minus 2r minus pi r. So I could divide everything through by 2. So if I do that, I get y is equal to 16 divided by 2, which is 8, minus 2r divided by 2, which is just r, minus pi halves r. So we want to go back in to what we're trying to maximize and replace it with this. And so we get the area over here is 2r times y, which we just said was 8 minus r minus pi halves r, plus 1/2 pi r squared. So let's distribute that 2r. So 2r times 8, that's 16r minus 2r squared. 2r times this negative pi halves r, the 2's will cancel. So that will give us minus pi r squared plus 1/2 pi r squared. I could combine like terms right now, but let's just take the derivative and then we can do that. So taking the derivative of the area, so derivative of 16r is 16 minus the derivative of 2r squared, that's minus 4r, minus the derivative of pi r squared, which is 2 pi r, plus the derivative of 1/2 pi r squared. So bringing that 2 down cancels with a 1/2, and we're left with just pi r. One way that we can write this, what a prime, another way to write it, right, is dA all over dr. In this way, it kind of shows you we're taking the derivative of a and what tells you what variable in that notation, what we took the derivative of. So we can combine like terms, and we want to find out when this is equal to 0. So we're looking at, let's see, 16 minus 4r, a negative 2 pi r plus a 1 pi r, that's a negative pi r. I'm looking at when is that equal to 0? Well, this is linear, so let's just subtract 16 on both sides. Actually, let's add 4r and pi r, so it's all just positive. So we would have 4r plus pi r equals 16. We can factor out an r here. They're like terms really, but because I want to keep it in exact form, I'm going to factor out an r. Well, that would give me 4 plus pi equals 16. So r is equal to 16 all over 4 plus pi. So we need to make sure that that is our maximum, where the maximum occurs. And so we're going to need to look at either taking the second derivative or looking at our second derivative test. So let's look at the second derivative. And let's use the second derivative test to do this. So looking at the double derivative of this area, the derivative of that 16 is 0. The derivative of negative 4r is just equal to negative 4, minus the derivative of 2 pi r is just 2 pi, plus derivative of pi r is just pi. So this is negative 4 minus pi. Notice there's no r in here that's left when we took the second derivative. Notice then that that value of that derivative is always less than 0. And so we know that a maximum is occurring at that value in here. To me, it would make sense not, yeah. Let's just leave, I'll just keep it as that. So that's where the maximum area occurs when r is this 16 plus 4 pi, all over 4 plus pi. We want to find what the maximum area actually is. So we need to do a little bit more work. We can go in here, we can figure out what y has to be. We know what r is. So let's go back in and figure out what y has to be. So right here, we are given that y is equal to 8 minus r. So 8 minus r, which is 16 all over 4 plus pi, minus pi halves times r, which again is 16 all over 4 plus pi. Okay, so let's get a common denominator so that we can add that. And so our common denominator I see is 2, 4 plus pi in parentheses. So that first piece, I don't have any piece of the denominator, so I'm going to have to take that 8 and multiply it by my whole denominator. So minus the next piece of my numerator, so that second term over here, I don't have the 2 there. So I'm going to have to take that 16 and multiply it by 2 to get the common denominator. And this piece right here, we already have that common denominator. And so we're just going to write it as minus 16 pi. So maybe we can clean it up some more. So y is equal to, let's distribute 16 in here. So 16 times 4, that's 64, plus 16 times pi is 16 pi, minus 16 times 2 is 32, minus 16 pi, all over this 2 times the quantity 4 plus pi. So notice how things kind of cancel out. 16 pi minus 16 pi cancels. We're left with a 64 minus 32, so that's positive 32, all over 2, all times 4 plus pi. And we can cancel a little further. 2 goes into that 32 16 times. So we get our y value is equal to 16 all over 4 plus pi. That's the same thing as r. So our maximum area we have A is equal to 2 times R. So 16 all over 4 plus pi times Y, which is 16 all over 4 plus pi plus 1/2 pi times R squared. So that's going to be a 16 all over 4 plus pi quantity squared. Notice they both technically have a 16 plus 4 pi, a 16 all over 4 plus pi quantity squared in common. So we can technically, if we wanted to pull that out, 16 all over 4 plus pi quantity squared. If we did that from that first grouping, we'd be left with just the 2. And from this second grouping, we would be left with that 1/2 pi, so plus 1/2 pi. Feet squared. So we got it in exact form, but if they wanted us, which doesn't make too much sense, right? If we wanted to figure out what that was, we could plug that into a calculator and have it do the work for us. Let me do that. I'll pause the video while I do that and write it out and turn it back on. So if you throw that into the calculator, you should see that the area is approximately 17.9 square feet. So we found the dimensions and we found the maximum area that we can get out of that window.